gonna finish our conversation today on volumes of, or using the washer method about the y-axis and other vertical lines. So we've been talking about rotating solids about the y-axis and other vertical lines, but now we're gonna notice that there's gonna be some pieces that are missing. So we'll start with an example. We want to rotate y is equal to x squared plus 1, y is equal to 1, and x is equal to 1. So the area enclosed between those curves just located in the first quadrant about the y-axis. So I kind of sketched out what this would look like here. I'm going to imagine, all right, well, what if I take this kind of triangular looking region and I rotate it about the y-axis? So I'll draw its kind of reflection over on the other side. It's pretty terrible, but hopefully you'll get the idea. So we're going to end up getting some kind of almost cylindrical shape with like some stuff missing in the middle. So you'll notice that that like white stuff right there is really like our negative space, that there's really nothing that's filling up that volume. So anytime we notice that there's going to be some missing piece or a missing area within the figure when we're rotating, that's when we want to use the washer method. So we talked about the washer method when we were rotating about the x-axis and other horizontal lines. We had used the formula that looks pretty similar to this. Volume is equal to pi times the integral. Before we were using a to b because we were talking in terms of x's. Now if we're rotating about a vertical line, we're going to be talking about y's. So we're going to be taking our outer radius squared minus our inner radius squared, and we're going to be multiplying that by dy. So we have a couple things to talk about in terms of this shape. Mainly the outer radius and the inner radius, and then we'll talk about the limits of integration as well. So if I were to take this original area that I had over here, that kind of triangular piece, and I wanted to know what its outer radius was and what its inner radius was, remember that when we're integrating in terms of y, we always read right to left. So when I'm figuring out what the outer radius is, I'm going to start at my outermost point on the right side. And remember, the outer radius is always the larger radius. So my outer radius is going to go from the outside out to the center here, because that's representing the radius of this figure when we rotate it about the y-axis. So my outer radius in terms of x's is going to be this x value of 1, because that's like the rightmost point that we're starting at. And I'm going to subtract the innermost x value, which is just 0 since we're rotating about the y-axis. So our outer radius just actually ends up being 1. And we can kind of see that we're 1 unit away from the y-axis. My inner radius is going to be a little bit different, because my inner radius, remember the inner one is always the smaller one. My inner radius is going to be from this inside function to the y-axis. So the inner function is just some x value here, some x value here, some x value here, and the x value is changing as we're going along the curve depending on where we are. So my inner is going to be some x value minus, again, my axis of rotation of 0. But we've been talking about this the last couple days. The problem is that when we integrate with respect to y, we need to know what x is. So I have an equation up here. My curve is y is equal to x squared plus 1. So I'm going to manipulate that so that I can know what x is equal to. So if y is equal to x squared plus 1, x squared would be equal to y minus 1. So x would be equal to the square root of y minus 1. So that's going to tell me that when I replace this x value with this x stuff, my inner radius is actually just going to be the square root of y minus 1 minus 0. Which is just obviously the square root of y minus 1. So I've got my outer radius of 1, I've got my inner radius of the square root of y minus 1, and I'm going to go ahead and start working with this integral piece. So my volume is going to be equal to pi times the integral from c to d. So now we need to know what y values we're working with. So over here we started at the y value of 1. So we're starting at a y value of 1. And we are integrating up to this y value up here, which, if we think about where x is equal to 1 and this or x squared is intersecting, that would be, I believe, at the y value of 2. So we're integrating from the y value of 1 to the y value of 2. Again, we can kind of confirm that graphically right here. My outer radius is 1 squared minus my inner radius of the square root of y minus 1 squared dy. I'm going to clean this up a little bit. If you want to just evaluate this as it is, you can. I'll clean it up to be pi times the integral from 1 to 2. 1 squared is just 1. And then the square root of y squared of y minus 1 actually just ends up being the quantity of y minus 1. Again, just be careful about if you are going to evaluate that. Make sure that you're pulling that stuff down in parentheses because the whole thing should be subtracted out. So that's going to give me pi times the integral from 1 to 2 of 1 minus 1 plus, or sorry, 1 minus y plus 1 dy, which we can combine those to be a negative y plus 2. And that's what I'd want to plug into my calculator. So when I do that, my volume should be approximately, let me see here, 1.5708. So that would be the volume if I were to rotate that little triangular piece around the y-axis. All right, so let's try another example. This time our region's going to look a little bit different. So I'll erase this whole thing to give myself some room to work here. All right, and my second example is to find the volume of the region enclosed by x is equal to y squared and x is equal to 2y. And we are also rotating that about the y-axis. All right, so a couple things here. I want to know what this graph looks like first of all, so I'm going to manipulate both of these equations to be in y equals. So if I take the square root of both sides over here, my y would be equal to plus or minus the square root of x. And over here, if I divide each side by 2, that's going to tell me y is equal to 1/2 x. So now I can kind of get a better idea of what these graphs are going to look like. It's going to be some sort of square root graph. It's going to be some sort of linear. So I'm going to go ahead and graph these. So I'll do the plus or minus square root of x first. So I'll graph the positive square root of x. That'll look something like this. And I'll do the negative part down here. Should look something like that. And then if I'm going to graph y is equal to 1/2 x, my y-intercept is 0. I'm going to count my slope of 1 over 2, go up 1, count over 2. So it should look something like this. And the part that's enclosed by these two graphs is going to be kind of this little, like, I don't know, weird looking shape here. So this part right here. So I don't actually have to worry about this stuff down there. I'm going to get rid of that because that's not really important to what I need to do in terms of rotating. So if I were to kind of think about that as being rotated about the y-axis, it would look something like this on the other side. I know I'm not kind of getting a very good representation on that side, but it should look something like that in our, if we kind of think about what this would look like in 3D. It's going to be a terrible sketch. Something like this. So then we have to think about our outer radius, our inner radius, and then our limits for our integration. So I'm going to start with my outer radius. So I'm thinking about my rightmost point of my curve here. So my rightmost point would be somewhere on this line, y is equal to 1/2 x. And again, since I am talking about this in terms of the function, my radius is extending to the y-axis. So I'm going to say that my outer radius in terms of y, because remember that we're integrating in terms of y, I know it's going to be this curve, so I'm going to say the outer radius is 2y minus the axis of rotation of 0, so that's really just 2y. My inner, again, the inner radius is going to be the smaller one, so the smaller one is met on the curve. That's that y is equal to plus or minus the square root of x, but in terms of y, that's the x is equal to y squared. And again, since I'm going to the y-axis, that would be y squared minus 0, which would just be y squared. So when I go to plug that into my volume formula, do my work down here. So volume is going to be equal to pi. My limits of integration, here I'm starting at a y value of 0, and over here I should be ending at a y value of 2, starting here, ending here. So my limits would be 0 to 2. I'm going to take my outer radius squared, so the quantity of 2y squared, minus my inner squared, so y squared, squared, dy. You can clean this up a little bit, I will. So make that into pi times the integral from 0 to 2 of 4y squared minus y to the 4th dy. And that's what I'd want to evaluate in my calculator. So that should give us an approximate volume of about 13.4041. That is a point there. All right, so that is rotation about the y-axis. We'll do a couple of examples with rotating about other vertical lines, and then I'll have you guys try a couple on your own. And you'll notice that some of the work that we're doing kind of relates back to the last couple of days that I've been having you guys practice volumes about the y-axis and about other vertical lines. So we will look at the third example. We want to enclose the region of y is equal to x squared. Y is equal to the square root of x. And this time we want to rotate about the line. X is equal to -1. All right, so these are both in terms of y equals, so I don't need to manipulate them before I see what this graph is going to look like. So make a quick sketch here. So I'll do x squared first. And then I'll do y is equal to the square root of x. So this should look something like this. All right, so then it looks like the region that we want to revolve is going to be kind of this petal-shaped region right here. And we are revolving this about the line y, x is equal to -1. So this is going to be our axis of revolution over here. Do this in a different color. All right, so if I were to kind of reflect that over here, that might look something like this. So the region will look something like that. And then if I kind of made that into a 3D, it might look something like that. All right, so let's talk about this outer radius and let's talk about this inner radius. So again, the outer radius, we want to start from the right to the left, and we want to talk about the outer in terms of what the larger radius would be. So if I start on my outer function is y is equal to x squared. But again, when I take that and put it into my integral, I need to make sure that's in terms of y, because we want to integrate with respect to y. So if I solve this out, that's going to tell me x is equal to the square root of y. So my outer function is y is equal to x squared, but when I manipulate it, it's going to be the square root of y. So my outer function is the square root of y. When I subtract the inner, now when I'm going to the inner part of my radius, the inner part is actually my axis of rotation at x is equal to -1. So when I do my outer, I'm going to be taking my rightmost part of the square root of y minus my leftmost point of -1. So when I clean that up a little bit, my outer radius actually becomes square root of y plus 1. My inner radius is going to happen from, again, the inner radius is a shorter radius, so it's going to be the inside function. So my inside function here is y is equal to the square root of x, but again, when I'm plugging that into my radius, I need to make sure that it's in terms of y. So if I square both sides, that's telling me that x is actually equal to y squared. So my innermost function is the y is equal to square root of x, but in terms of y, x is equal to y squared. And if I extend that to my axis of rotation, that's going to tell me that I'm going to take my outermost function of y squared, and I'm going to subtract the inner of -1, because again, the inner is our axis of rotation here at -1. So if I clean that out, my inner radius would actually be y squared plus 1. All right, so let's talk about this integral. So volume is going to be equal to pi times the integral from here. I'm starting at a y value of 0. Up here, I'm meeting at a y value of 1. So 0 to 1. My outer radius, square root of y plus 1 squared minus the inner radius of y squared plus 1 squared dy. Not much I can really clean up here unless I want to FOIL things out, and I'm not going to. I can just use my calculator to help me evaluate. So the volume here should be approximately 3.0369. All right. So we will do one more now when our axis of rotation is actually on the other side. So our axis of rotation has always been on the left side of the function. And now we'll flip it around and see what happens. All right, so our last example is going to be to take y is equal to the square root of x, and we're going to bound that by the lines y is equal to 0 and x is equal to 3. And we are going to rotate that about the line x is equal to 6. All right, so everything's in terms of things that I can graph, so I'm not going to need to do any manipulation here. All right, graph the square root of x first. 1, 2, 3, 4. That's 1, 2. All right, so here's my graph. Y is equal to the square root of x. I'm bound by the line y is equal to 0, so that is going to be my x-axis. And I am also bound by the line x is equal to 3. So it looks like the region that I want to revolve is actually happening right in here. All right, so I can get rid of the rest of this piece here because I don't really need that. All right, and my axis of rotation is about the line x is equal to 6. So here is my axis of rotation right here. All right, so if I were to kind of sketch that out quickly, that's probably going to look something like this over here. Kind of a big spread out space here, but maybe something like this and like this. It's a terrible 3D drawing, but you get the idea. All right, so now we need to talk about the outer radius and the inner radius. So this is going to look a little bit different than the other one. So when I'm talking about the outer radius, I'm actually going to be talking about the radius from, since my axis of rotation has kind of flipped over on the other side in this problem, I'm going to start my outer radius from the rightmost point. Here, the rightmost point before I rotated was on this line x is equal to 6. And again, the outermost radius is always going to be the larger radius. So if I'm thinking about where the largest part of the radius is, if I extend this over to the edge of my graph, my outermost radius starts at the x value of 6 and extending to this piece of the line y is equal to the square root of x, or not the line, it's a function. But again, when I'm plugging that into a radius, I need to make sure that this is in terms of y, because when I integrate, it's got to be in terms of y. So I'm going to rewrite this. If I solve for x here, x is going to be equal to y squared. So I'm going to write this as 6 minus y squared. Again, 6 starting at the rightmost point, extending out to the largest part of my graph here, and that's the curve y is equal to the square root of x. My inner radius, again, is going to start at the right here, but my inner radius is going to extend to just kind of that point where we cut off our graph or our curve. So here, I'm starting at 6, and the x value that we cut off the curve was actually at 3. So my inner radius is actually just 3 units, which we can confirm. There's 3 units in between this line x is equal to 3 and x is equal to 6. So let's go ahead and start setting up this integral. So b equal to pi times the integral. Here we started at the y value of 0. But up here, this is where our limit of integration is going to be, since that's where our curve extended to. We know that this curve is y is equal to the square root of x. And here we know that our x value is 3. So if y is equal to the square root of x and the x value is 3, that must mean that the y value at this point would be the square root of 3. So we're integrating from 0 to root 3. My outer radius is going to be 6 minus y squared squared minus my inner radius of 3 squared dy. I'm just going to clean this up in one step. So pi times the integral of 0 to root 3 of 6 minus y squared squared minus 9 dy. And I'll just use my calculator to evaluate that. And that should give us a volume of approximately 91.4155. All right, so now it's your turn to do a couple of problems. Let me know if you have questions.